Future research in quantum theory is set to open up new frontiers, which could completely change how we understand the universe. Welcome to our session on Introduction to Quantum Theory. Today, we're going to explore some mind-bending concepts that have changed the way we think about the universe. So, what is quantum theory all about? Well, it shook up the world of physics by introducing ideas that really challenged the traditional views of classical mechanics. It gives us a whole new way to understand how matter and energy behave at the tiniest scales, think atoms and subatomic particles. This framework opens up fascinating insights into the very nature of our universe. Now, let's see how these concepts play out in real-world applications. Let's take a moment to explore Max Planck, a brief biography. This remarkable physicist has left an indelible mark on the world of science. Max Planck was born on April 23, 1858, in Kiel, Germany. He was a pioneer in theoretical physics, especially known for his groundbreaking work in quantum theory. In recognition of his incredible contributions, Planck was awarded the Nobel Prize in Physics in 1918 for his discovery of energy quanta. Let's take a look at the late 19th century physics, a fascinating time in the world of science. During this period, classical physics was king, with Newtonian mechanics and Maxwell's electromagnetic theory leading the way. But here's the twist: some phenomena, like blackbody radiation and the photoelectric effect, were throwing a wrench in the works. These mysteries hinted that it was time for fresh ideas and new approaches in physics. Let's jump into the intriguing world of the blackbody radiation problem. This is where things get really interesting. So, picture this: physicists were scratching their heads over blackbody radiation. Classical physics was predicting an ultraviolet catastrophe, suggesting that energy radiated at short wavelengths would just go off the charts. This conundrum really shone a light on the limitations of classical theories. It sparked a quest for new ideas and frameworks to better understand the universe. Let's kick things off with Planck's hypothesis. Max Planck shook the scientific world with his groundbreaking idea that energy is quantized. He introduced us to the concept of energy quanta, suggesting that energy isn't just a continuous flow but comes in discrete units. This was a game changer for how we understand energy exchange. Let's kick things off with Planck's law of radiation. This is a fascinating topic that lays the groundwork for understanding how energy is emitted in the form of electromagnetic radiation. So, what exactly is Planck's law? It mathematically describes how a blackbody, an idealized physical object, emits electromagnetic radiation when it's in thermal equilibrium. This law was a game changer, solving the blackbody radiation problem and introducing us to Planck's constant, which is a key player in the world of quantum mechanics. Let's explore the implications of Planck's work and see how it reshaped our understanding of the universe. Planck's groundbreaking work had some pretty big implications for physics. It set the stage for quantum mechanics, shaking up the classical view of energy distribution and opening the door to a whole new understanding of atomic and subatomic processes. Let's jump into the rise of quantum theory, a fascinating journey through the world of tiny particles and big ideas. First up, we have evolution. After Planck's groundbreaking discovery, quantum theory took off, thanks to the brilliant minds of physicists like Albert Einstein, Niels Bohr, and Werner Heisenberg. Can you imagine the excitement in the air as these ideas began to take shape? Now, let's talk about the impact of these developments. They completely changed how we understand atomic structure and interactions, paving the way for what we now know as modern quantum mechanics. Let's talk about Einstein and the photoelectric effect. This is where things get really interesting. So, Albert Einstein took the ideas of Max Planck and ran with them. He explained the photoelectric effect by suggesting that light is actually made up of tiny packets called photons. This groundbreaking work not only provided more proof for the idea that energy is quantized but also earned Einstein the Nobel Prize in Physics back in 1921. How cool is that? Let's jump into Bohr's model of the atom, a fascinating concept that changed how we understand the building blocks of matter. Niels Bohr brought us a groundbreaking model that combined quantum theory with atomic structure. He explained how electrons orbit the nucleus in specific, quantized paths, shedding light on the mysterious spectral lines we observe. This was a huge step forward in applying quantum principles to the world of atomic physics. Let's explore the fascinating concept of wave-particle duality. This idea is at the heart of quantum mechanics and really shakes up how we think about the behavior of particles. So, what exactly is wave-particle duality? Well, it suggests that particles, like electrons, can act both like waves and like particles. This dual nature is a fundamental part of quantum theory and really challenges our traditional views on how waves and particles behave. Isn't that mind-blowing? Let's jump into the fascinating world of Heisenberg and the uncertainty principle. Take a look at this illustration. Werner Heisenberg introduced the uncertainty principle, which tells us that we can't know both the position and momentum of a particle at the same time. This idea really shakes up our understanding of how particles behave at the quantum level. Now, check out this graph. The uncertainty principle shows us the limits of what we can measure in quantum mechanics, highlighting just how probabilistic the quantum world really is. Let's talk about the legacy of Planck's work. This is where we see the ripple effects of his groundbreaking ideas. Max Planck's pioneering work on energy quantization was a game-changer, setting the stage for quantum mechanics. His contributions have not only transformed physics but also continue to shape fields like quantum computing and theoretical physics today. Welcome to our exploration of contemporary applications of quantum theory. Let's uncover how this fascinating field is shaping our world today. First up, we have quantum computing. This groundbreaking technology uses the principles of quantum mechanics to tackle complex computations at lightning speeds, making waves in areas like cryptography and data analysis. Next, let's talk about quantum cryptography. This innovative approach provides secure communication methods rooted in quantum principles, ensuring that our data remains safe from prying eyes. And we can't forget about medical imaging. Technologies like MRI are powered by quantum mechanics, giving us detailed insights into the human body and significantly improving our diagnostic capabilities. As we wrap up our discussion, let's turn our attention to the conclusion and future directions. Looking back at our journey through the historical context of Planck's work in quantum theory, it's clear that his contributions have made a huge impact on science and technology. And guess what? Future research in quantum theory is set to open up new frontiers, which could completely change how we understand the universe.
Thanks for listening to the Wonders of Science channel, where curiosity meets discovery. Stay tuned for more fascinating insights into the mysteries of our world. Keep exploring, and until next time, never stop wondering.